Hello viewers, myself Dr. Mahantesh K, Associate Professor, Department of Electronics and Communication Engineering, SJB Institute of Technology, Bangalore. Welcome you to this pre-recorded video sessions on electromagnetic waves. Introduction to Electromagnetic Waves, Module 1, Class 4. In this video, you are going to study about electric field intensity and computation of electric field intensity on various charge distributions. So in my previous video, we have derived electric field intensity. So if we consider one charge fixed in position, say Q1, and if we try to move a second charge Q2 in and around the charge Q1, the force on charge Qt is given by Coulomb's law. Ft is equal to 1 over 4 pi epsilon naught Q1 Qt by R1t square in the direction A1t. So we can write the force equation as force per unit charge given by F over Q is equal to 1 over 4 pi epsilon naught Q1 by R1 square in the direction A1t. Now we have defined the electric field intensity as the vector of force on a unit positive discharge. So we can also define electric field intensity as force per unit charge, and it is measured in terms of newtons per coulomb or volts per meters. The field of a single point charge can be written as E is equal to 1 by 4 pi epsilon naught Q by R square AR in general, where AR is a unit vector with its magnitude 1 in the direction from the point at which the point charge Q is located to the point at which E is desired to be measured. This is an electric field intensity in a vector form. Suppose if you want to measure electric field intensity due to two or more point charges, say Q1, Q2 and etc. located at the distances R1, R2 etc., then the sum of electric field intensity on Qt caused by Q1, Q2 etc. acts like a superposition principle where it will be the summation of all the electric fields due to various point charges located from particular distance from the point P, and it will be a simple summation of all the electric fields measured at some point. This is an example which we have discussed in a previous video. So just a quick review of this example, like you've been given a charges Q1 of 2 microcoulomb located at P1 and a second charge of 3 microcoulomb located at P2, and you need to find electric field at some point M 3, minus 4, 2 coordinate axis values, and you'll be getting 623.7 AX minus 879.92 AY plus 160.17 AZ volts per meter. Now let us just try to find the field due to a continuous volume charge distribution. If we now visualize a region of space filled with more number of charges separated by minute distances, such as the space between the control grid and the cathode in the electron gun assembly. So we denote the volume charge density as rho v, having the units of coulombs per cubic meter. The smallest amount of charge delta Q in a small volume delta V can be given as delta Q is equal to rho V delta V, where rho V is constant. We may also define rho V, that is charge density, mathematically by using a limit of the above equation, limit delta V tends to 0, delta Q divided by delta V, where rho V is constant. The total charge with some finite volume can be defined as Q is equal to volume integral rho v into dv. Example, find the total charge inside the volume indicated by rho v is equal to 4xyz square, where rho varies from 0 to 2, phi varies from 0 to pi by 2, and z varies from 0 to 3. All values are given in SI units. So as I've explained in the previous slide, calculate x is equal to rho cos phi, y is equal to rho sin phi, and rho v is equal to 4 pi 4x y z square. So I'm going to substitute the values of x, y, and z square. And we know that from the previous derivation, Q is equal to the total charge is equal to the volume integral with respect to the volume charge density with respect to the volume. So this volume is represented in terms of triple integral of values or limits varying from z equals to 0 to 3, it's given, phi equal to 0 to pi by 2, and rho is equal to 0 to 2. And substitute rho v and dv. What is the differential volume? So it is d rho d phi, and dz of a given cylindrical coordinate system. Since the coordinate axes were given as rho phi z, so I have assumed the dv as in the cylindrical coordinate system. Now solving this integral part, you'll be getting the total charge is equal to 72 coulombs. The contributions of all the above volume charge in a given region. So let the volume element delta V approaches 0 is an integral in the form of ER is equal to volume integral 1 over 4 pi epsilon naught rho r square dV divided by r square into this r minus r dash over r minus r dash is nothing but a unit vector. So now let us just try to calculate the electric field due to a line charge. So till this point, we have considered two types of charge distribution, the point charge and charge distributed throughout the volume with a density rho v coulombs per meter cube. Now, if we now consider a filament-like distribution of volume charge density, such as a very fine sharp beam in a cathode ray tube, or a charged conductor of very small radius. Let us assume a straight line charge extending along the z-axis from minus infinity to plus infinity. We desire to compute the electric field intensity at any point resulting from a uniform line charge density rho L. Suppose if I consider the point at the point P, the incremental field of dE has the components in a rho direction and az direction and no a phi direction. The component of dEz is the result of symmetrical computations of line segments above and below observation point P. Since the length is infinity, they are cancelling each other. So there is no Ez component in the direction z-axis. So the component dEz is equal to 0. Therefore, what is the remaining component? There exists only dE rho. And from the Coulomb's law, we know that dE rho will be inversely proportional to the distance to the line charge rho. Consider a point P with the coordinate axis values as 0, y, 0. Therefore, r dash is equal to z a dash, r is equal to y a y, which is equal to rho a rho. Therefore, given electric field, differential electric field due to a differential line is equal to 1 over 4 pi epsilon naught dq of r minus r dash over magnitude of r minus r cube. which is equal to 1 over 4 pi epsilon naught rho L dz. So dq is equal to rho L dz dash rho a rho minus z a z divided by rho square plus z dash square over the power or the root 3 by 2. Once I solve this, rearrange these components, I'll be getting 1 over 4 pi epsilon naught rho L rho a rho dz dash over 4 pi epsilon naught rho square plus z square 3 by 2. Now, since the line conductor varies from minus infinity to infinity, therefore the total electric field in the direction with respect to the rho is computed in terms of integral of minus infinity to plus infinity of dE. So what is dE? dE is going to be substituted inside the integral as 1 over 4 pi epsilon naught rho L d z dash into rho divided by 4 pi epsilon naught into rho square plus z square to the power 3 by 2. So using this formula, the integral formula du by square root of 3 by 2 root of a square plus u square, we can obtain this equation. So now, taking the integral and substituting the limits, I'll be coming to the conclusion that E rho is equal to rho L divided by 2 pi epsilon naught rho. So this is the electric field intensity with respect to the field of a line charge. Now let us just try to analyze the answer itself. So what is E is equal to rho L by 2 pi epsilon naught rho a rho? The field falls off inversely with the distance to the charged line as compared with the point charge where the field decreased with the square of the distance. Let us just try to solve a simple example of calculating a field of a line charge. Assume an infinite uniform line charge of 5 nanocoulomb per meter lie along the positive and negative x and y axis in free space. Find electric field at the point PA and the point PB. So now is that given line falls in the positive and negative x and y axis. So this appears to be the line and the red and the two given points PA and PB are located as given in the figure. So now to calculate the electric field intensity at the point A, so this is the equation. I'm going to substitute all the values and I'm going to obtain electric field intensity at point A is equal to 44.939 AZ volts per meter. Whereas electric field intensity at point B due to the line charge of 5 nanocoulomb per meter. And I'll be getting the answer as 10.785 AY plus 36.85 AZ volts per meter. Rho is the shortest distance between an observation point and the line charge. Thank you for watching this video. Hope you have enjoyed electric field intensity and uniform charge distribution considering a volume charge density and a line charge density.